Hello everyone. In this video, we are going to talk about some basics and some important terminologies in optimization. So the foremost topic or item that we need to talk about is the objective function. This is the function that you are trying to optimize. You are trying to find the minimum or maximum of it. And then, of course, it has some variables in it that they are under your control. You can change them, so we call them control variables. Okay, so let's say, for example, I have an object, right? And it's like a shaft, a cylinder. And the material of it has a specific strength, right? So it has some specific strength SY. So you already chose your material, aluminum, steel, whatever. And then you apply some force on it. And this force you have to basically bear with this object, so you cannot change this, right? So this F is also fixed, this tensile force F. And as I said, the material is already fixed. So all you can change is the diameter of this shaft D, right? So now the question is, how much of diameter would you select so that under this load F and with this material selected, this shaft does not break, right? This cylinder does not break, or it does not go to plastic deformation. As you know, in solid mechanics, this is what we call the yield strength. So as long as the stress is below this number, that's where your material will not have permanent deformation. In other words, if you let this force F go, if the force disappears, then the material that was elongated a little bit due to this tensile force, the elongation goes back to zero, okay? So here, let's say I just want this machine to work. This shaft is a part of a machine, and this load is due to the reaction with other members, components of the machine. And so when, let's say, the machine is off and this force F goes away, I want the shaft to go back to its original length. So what I want is the sigma, the stress, the normal stress in the shaft, which is defined as F over the cross section of the shaft. This should be what? Less or equal to the strength of the part divided by some number we call safety factor, right? So now let's say my goal is to make the part as safe as possible. So if I define my safety factor to be something that I'm interested in, my cost function, your safety factor, and if I use this equality side of it, right? So I can have an equality or an equation for this safety factor. If I use that, I will get safety factor to be equal to, if you just do a simple change of numerators and denominators, right? Then you will get safety factor to be A times SY divided by F. And if for this A, you replace pi over 4 times D squared, right, based on the diameter, this is going to be pi SY D squared divided by 4 times F. Okay, so you clearly see your cost function, the thing that you are interested in changing it, and in this case making it as large as possible because you want to be as safe as possible, is the safety factor. This is your cost function. And since your material is chosen, SY is fixed, and since your machine operation gives you a fixed F in this case, then the only thing you can change is really D. So this D is your what? This is your control variable. That's the only thing that you can change in this case. And this safety factor is your cost function. This is what you need to control in this case and make it as large as possible, change and make it as large as possible. Well, in this case, you're not going to have a real optimization problem. Why? Because as I mentioned here, an optimization problem only happens when there are at least two factors working against each other in real world, or your function, your cost function, even if you have one variable, it has really an extremum point, a maximum or minimum. If your function is monotonously increasing or decreasing, then you will not have an optimum point. You will not have an extremum, right? In this case, if you look, if I make D larger, so I use a bigger shaft, definitely it makes what? My safety factor bigger and bigger. So there is no limit. I can make the shaft as large as I want, and by that, I make my safety factor as large as I want, right? So the relation here between D and the safety factor is monotonously increasing like this. It's a square function, correct? As you can see. So there is no maximum or there is no minimum point that I can choose. Why? Because my cost function has only one factor affecting it, and that is the geometry. And of course, the thicker I use the shaft, the better condition in terms of safety it's going to have. So that's not a real optimization problem, okay? As I said, you need at least two factors working against each other. Like in this case, what could be something that limits how large of diameter you can choose? Well, two things. One is the cost. Of course, the more material you use, the bigger chunk of, let's say, steel or aluminum you use, you have to pay more. And when you're designing, it's not just that you care about what? Care about just safety, you also have to care about the cost and economy. So in here, maybe you need to consider another factor, and that is the cost or the price of material, correct? So what can you consider? Well, you know, the material here, you can measure it by volume, and the volume of the cylinder is also proportional to D squared, correct? So let's say it is N times pi over 4 D squared times L, where L is the length of this cylinder. If, let's say, you consider this L also to be constant, and D is the only thing you can change, this is the volume, and N is the price of that material per volume, let's say per cubic inch, per cubic meter, or whatever. So you want now this guy to be what? As small as possible. At the same time, you want this other function to be as large as possible. Okay, so your real cost function should be a combination of this price, let me call this P, for example, right? Price of material, PM. This PM and this safety factor, you have to combine into a new cost function. One of them is working what? Against increasing the diameter. One of them needs the diameter to go up. So if you can combine this together somehow, then you can come up with a more logical way of approaching it, right? So maybe you need some new cost function now, F of D, to be what? To be a linear combination of these two functions. Maybe it is like safety factor plus another number that determines the weight between these two. You might call it lambda, and then times the price per price of the material. Okay, so again, lambda determines the weight of one with respect to the other. It depends on how much one is important to you compared to the other. Maybe you are really tight in budget, so you have to increase the lambda, right? Maybe you're not tight in budget, you are really careful about the safety because it's a dangerous machine, and if it fails, you might have some severe consequences. Then you have to make lambda smaller, right? So safety factor shows itself bigger. We'll see, we'll talk about this combination of functions and these weights. In this case, we call this guy a Lagrangian multiplier, and we're going to have a separate video on that. But in general, when you combine like this, now your function might have a minimum or a maximum, okay? In this case, really not necessarily, because still it is going to be a function of d squared, okay? Right? So it's not going to be that simple in this case. It's still going to be, as I said, a function of, unless you just say, well, it might just be some other thing that I have to consider. So your function is not pure d squared, because here this is like a times d squared, this is like b times d squared. When you combine, the whole thing is going to be like c times d squared. So it is still not going to show any max or min, right? So you need probably some constant added, or you need some linear term. You definitely need a linear term of d added. So that will help you find a maximum or minimum. Okay. Another example I want to talk about here is driving in a car. So when you drive with your car on the highway, the efficiency or the fuel economy does depend on how fast you are driving. Okay, so, and it depends on the car, it depends on what kind of fuel the car is burning, but in general, it's not like the slower you drive, the better fuel economy you're gonna have, or the faster you drive, you're gonna have better fuel economy. You probably see in many cars, they say street mileage and then highway mileage. And most of the time, the highway mileage is higher. That's right. But they are assuming that you are not over speeding. So they assume that you are probably going 50, 60 miles an hour or so. If you are in the range of 80, 90, 100 miles an hour, then your fuel economy is going to be probably as low as when you are driving 20 miles in a small street. Okay, and what's the reason? The reason is there are two factors here. One is when you're driving a little bit faster, the lubrication of the machine is done better. Why? Because the oil that is used for lubrication, when the temperature is a little bit higher, they have a lower viscosity and the friction in the machine goes down a little bit, okay? So you can have better economy because you have smaller friction. That's fine. But when you are running too fast, now you have a lot of expansion, right? And your combustion is happening so fast that you have a good chance of not burning all of the fuel that is inserted into the chamber and losing it a little bit. The chance of leaking goes up. You have a better chance of rolling resistance showing itself, although it's not that hugely depending on the speed, but the air drag does. You know, the air drag on your car depends on your velocity squared or speed squared. So the faster you drive, you have more friction from the air around the car, and that means you're burning a lot of fuel just to overcome that air drag. So it's a combination of several factors: lubrication, thermal expansion, rolling resistance, air drag, and so many other things that they are all working together. And if you can draw a plot of miles per gallon versus your speed, you're going to see a curve with a maximum. So it says, for example, for the Ford F-150 pickup, right? If you want to get the maximum fuel economy, you should be driving around 50 miles an hour, right? For, let's say, a Hyundai Sonata, you are driving about 30 miles an hour to get your max fuel economy. Okay, so there are several factors working against each other. The same thing that I mentioned here. If you make diameter bigger, you get better safety factor, but at the same time, you are getting a poor cost or economy which is working against you. So you have to have several factors, one at least working against other, so you have a maximum point or a minimum point, right? Or as a last example, because they might be so much mechanical related, let me just give you one more example, and that is just pure geometry, right? So if I say, okay, I have a rectangle, what is the let's say, what is the maximum area of this rectangle? If it has two parameters, right, length and width, L and W, if I say A of L and W, that's my cost function, which is L times W, I want to maximize this cost function A. How would you do that? Well, there is no limitation here. You can make L as large as you want or W as large as you want. What's the limitation here? There is no limitation, right? Unless you come and say, I want my area to be max, but it is subjected to ST some constraint. So now that's the topic of what? Constraints. So if I don't provide that, my optimization problem is unconstrained. And again, there is no optimization because I can make it as large as I want. But if I provide the constraint, say the perimeter of the rectangle, which is 2 times L plus 2 times W, is a constant number, let's say 10 units, 10 meters. Now you have a constraint. Now you cannot change L and W as large as you want because the sum of them really in this case is limited, right? Here you can simplify it 2 and get L plus W equals 5. This equality constraint is what will make this an optimization problem, okay? So now from here, let's say you can what? You can find one of them. Let's say, for example, W is 5 minus L, right? And then plug it back into the relation of A. So if you plug this back into A, now your A is going to be what? L times 5 minus L. And it is going to be 5L minus L squared. And if you plot this function, now this function will have a what? Will have a maximum. Okay, so first of all, this is 0. This max point is 2.5. And the maximum L can have is 5 because otherwise A gonna go negative. So the maximum is going to happen when L is 2.5, and that means also W is 2.5. In other words, when this guy is a square, really, right? Among the rectangles with the constant perimeter, the one that is a square is the maximum area, correct? This is a well-known geometry optimization problem. So you see here, I have a max due to having this constraint here. That's the main thing, having a constraint. So optimization problems can have constraint or they might not have any constraint. And you might say, well, in this case, if you remove that constraint, there will be no optimization. You are right, but it's not all the time like that. There are some problems where there is no constraint, still you have optimization problem. Like what? Like if you look at the video I published earlier, we looked at this problem. We have this function x1 squared plus 3x2 squared. So here my function, cost function, is a function of two cost control variables, x1 and x2, and the goal was to find the minimum of this function. It was not subject to any constraint, and in this case, you can show that the minimum is at 0 and 0. And so please watch the video that I published on the steepest descent, or you might call it gradient descent, which is an unconstrained optimization. Okay, so there was no constraint on it, and I could find the minimum. Why? Because my cost function did have really an optimum point, a minimum point, okay? So you could have problems without constraints, still they are optimization problems. Or they can have constraints. Now, about the constraints could be hard or soft. What does that mean? Well, constraints that are hard are the ones that you cannot violate under any condition. For example, let's say in this mechanical design example that we have, this shaft that you're designing is what? It is inside some slot, and the size of this slot or this groove is D1, okay, and this is a fixed number. So this shaft should always work inside this guide, this slot, groove, whatever you want to call it. And the size of this slot is fixed, is given to me. So although I have some function here that I need to optimize, I need to make sure my D, whatever number I choose for D, should be less than what? D1. This is called a hard constraint. Why? Because I can never ever violate it. There is no chance for me to allow me violate this constraint, because otherwise my mechanical system will not work, correct? That is called a hard constraint. It's not, cannot be violated. In this example of the rectangle thing, what was your limitation? So if when you change this, it was, if you remember, it was 5L, right, minus L squared. What's your limitation here? Limitation is L has to be bigger than or equal 0, right? L cannot be negative. If you ever find a number here which gives you a negative L for a max or min or whatever, that is violating the physical sense of this problem. You cannot have a rectangle with sides of negative numbers, right? Because instead of, remember, 2.5 and 2.5 that we had, we might find a case that, let's say one of them, because some of them has to be 5, one of them is like -1, the other one is 6, or this one can be -6, this one can be, let's say, positive 11, correct? Still some of them is 5. Well, this solution is not valid because it means there is no rectangle. So hard constraints cannot be violated. What about soft ones? Soft ones are the ones that you can violate, but you better not. So if you violate them, it's not going to have a direct physical consequence like this, like the shaft does not work in the slot or there is no rectangle, but you better not violate them, correct? So it's the difference between must and should. So hard constraint must not be violated. Soft constraint better or should not be violated, right? But if you do, there is what? There is what we call a penalty. So in order to discourage that, we try to add a penalty term. And here is what probably you can see in this optimization problem of the shaft design. This is what you really want, correct? What you really want is to improve the safety factor. And you also have a hard constraint here, which is D should be less than D1. So this is your real cost function, actual one that you absolutely care about. This is your hard constraint, but you have what? You have some limitation on the budget. You cannot just make it as expensive as you want. So here you try to add that penalty term to the original cost function, correct? To discourage this increase in the cost, correct? Right? You have to discourage that. So it means if I make my D bigger, this cost goes up, and to discourage that, your lambda here has to be negative, or what you can do, you can say this guy can be negative. So if my D goes up, it helps my safety factor raise, but this term that is cost and is prohibitive, it's going to go down, so the whole thing will bring down my function. Okay, so you can consider this like a what? Like a penalty term. right? So you're not, with this penalty term, you're not setting a hard limit on D and say, hey, never make D bigger than that. No, why? Because if you even make D a little bit bigger or smaller, I can still afford it probably. I'm not super badly tight on the budget, but I discourage you to make it super large and over-design the part, right? Another example that you can see is what we call in machine learning, we call it regularization. What is this? This is when you are trying to do a fitting of a model to some data, and that model has a bunch of parameters in it. So you can even include it in curve fitting problems, right? So let's say you have a bunch of data here, and let's say you try to fit a cubic function, correct? A model of cubic function. So y equals like w naught plus w1 times x plus w2 times x squared plus w3 times x cubed, right? And you have a bunch of data points. Let's say the data points are xn and yn, correct? And n goes, or xi and yi, I goes from 1 to n, right? So you have n data points. And you want to fit this cubic model to those data. So if you watch my video on curve fitting, you see that basically the thing I try to minimize is an error function, correct? Where error is really the vertical distance between each point and the corresponding location on the curve. So let's say here, if I have a point like this, and this is the corresponding projection on the curve, what I really try to minimize is this vertical distance ei, which is yi, and then the difference of that at y at xi. Or you might call it y hat, and y hat is what comes from this function. Okay, so what you're really trying to optimize your cost function f of vector w is what? It is the summation I from 1 to n of yi hat minus yi squared, right? This is called least squares curve fitting. Here, vector w is a vector that involves all of these four numbers. Y hat I here is plugging xi into my fitted model, which is w naught plus w1 times xi plus w2 times xi squared and plus w3 times xi cubed. And yi is just a given number. So this is what you're trying to what? Optimize. And when you do that, it will give you a formula, which I mentioned. It's a matrix formula that gives you a set of W's. Now, one of the things that you do in this regularization is you try to choose as W's as small as possible. So here, all I need for my W's is to minimize the sum of squared vertical deviations. But one of the things they do, typically, they want these W's to be as small as possible. So what do? They add an extra term here, which is summation of wi squared, and here I goes from 1 to 4 because you only have 4 W's. And they add that to the original cost function with a weight of lambda. So here, although I can have several different sets of W's to help me minimize the error, I only choose the ones that have a minimal norm, right? I choose those W's that are as small as possible. Okay, So I'm discouraging you to give me large weights for W0, 1, 2, and 3. I'm only asking you, give me W's that make this error go down and be as small as possible, yet those W's themselves are as small as possible. So this is what we call a penalty term. So I'm discouraging large weights. I am interested in small weights that make my error go down. Okay, so this is called a penalty term, or term really, not terms. And this is what we call the Lagrangian multiplier, which, as I said, we're going to have a separate video on, so no worries. So this penalty is quite clear. And that's how we try to penalize soft constraints, right? So here my soft constraint is make W's as small as possible, right? That's a soft constraint. It doesn't mean if my W0 instead of 1 becomes 1.5, the system would collapse, or the mechanical system like this is not going to work. So that's the difference between hard and soft constraint. Good. A couple of other things I need to mention about optimization. One of them is the difference between feasible solution, optimal solution, and Pareto-Optimal Solution. So what's the difference between them? If I go back to that rectangle problem, if you remember, A was L times W, and I had L plus W times 2 was equal to 10, okay? So this is my cost function, this is my constraint. Now, optimal solution, if you remember from here, from the constraint, I found one of the variables, plugged it back into the cost function, make it a function of one single variable, and then I can take a derivative from that, set it equal to 0, as you know in calculus, and find what? Find the optimum point, correct? So that's the optimal solution, means the A, that there is nothing bigger than that. Again, right? Just very fast from here, I found my W, plugged it back in here, so I get 5L minus L squared, and then, as you know, in calculus, I took the derivative of A with respect to L, set it equal to 0, and that gives me the optimum solution for A, right? If I plug it back into A, my A star, the max is going to be 2.5 times 2.5, which is 6.25, correct? So if I plot my function A versus L, correct? The peak point, the maximum point here is 6.25. There is no other possible value of A in this problem that can go beyond 6.25. So this is what we call an optimum solution. Now, what is a feasible solution? Feasible means as long as it satisfies the constraints. So do I have any constraint here? Yes, if you remember, I told you in this case, L has to be bigger than or equal 0. That's a hard constraint. I cannot have negative L's. So for example, if I don't go with 2.5, 2.5, if I go with, let's say, 4 on L, correct? If I choose L to be 4, which means clearly W has to be 1, because some of them is 5, and then A from here, which is the product of the two, is 4, right? How about this point? Is this point a solution? It is a solution, but it's not the maximum, it's not the optimum solution. So this is your what? This is your optimum, maximum in this case, solution. But this one here, which still, this L of 4 is bigger than or equal 0, so it is still satisfying my hard constraint. It is a what? And it is satisfying this constraint, which is L plus W equal 5, correct? Right? That's why W became 1. So this solution here satisfied both of my constraints. So, but it's not the maximum. So this is what we call a feasible solution. And we're going to see this later in several techniques of optimization, especially in linear programming. I'll talk about feasible solution. So just wanted to tell you feasible and the ideal goal is to find the optimum solution. This is optimization. So the goal is to find optimum, but sometimes your algorithm might not in the first try or so give you the best solution. It just gives you a solution that just does not violate the constraints. So just keep this terminology in mind. Pareto-optimal is what? Pareto-optimal is when you cannot really find any optimum solution. And the reason for it is there are several factors working against each other, and no one can dominate the other factors. No factor can dominate the other factors. They're all working against each other, but there is no domination. Like what? For example, let's say here, so let's say in summer, you have 30 days in, let's say, June, and you are working some part of that 30 days, and the rest of the days you are taking off for a vacation. So, how would you decide how many days you would work and how many days you would take off? The thing is this, the more days you work, the more money you will have to spend on your vacation. Okay, so you can have basically, you can spend more in your vacation, right? You can go to more expensive restaurants, have higher end entertainments and so on. But at the same time, the more days you work, the fewer days you have to spend for your vacation. So how would you really decide, right? It is not super easy. Now, it might be a personal choice that you say, well, I do not care if I have really high-end entertainment, restaurants and everything. I just want to be as many days off as possible. Then yes, that's an easy solution. Or the other way around. When I go to a trip, when I go to vacation, I just want to do whatever I want. I want to spend as much money as I want. Then for that, you need to have a ton of money, and for that, you need to work a lot of days, which does not leave you with so many days off. So if you really want to get both, right, both have a luxury, basically, vacation, and also not overwork yourself for most of the days of the month to just get that money, it's not really an easy solution to get what? To get the maximum joy here versus the number of days working. So if the variable that you're deciding is the number of days working, and this is joy, because joy is something hard to really define, it's not really easy to go 1 day to work all the way to what? 30 days to work. Of course, 30 days is definitely not a good thing, because then you don't have any. And 1 day is not good because you don't earn too much money to spend. So probably, right, if you look at one might not give you a lot of joy, and 30 might not give a lot of joy, right? So, but your function might not be exactly like something like this, correct? It might not be exactly like a parabola like that says 15 days is the best. No, it depends in this joy, which is a sum of luxury and time. How you would weight them, how you would combine them, maybe it's not just as simple as this. So in the beginning and the end, there is definitely not any good solution for me, but in between, right? in between, maybe you have a different type of behavior, right? Maybe, for example, you have some area like this. So it goes up a little bit, but here is kind of flat and then goes down. So do I select here, 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 or here? 10 days, 15 days, 20 days, 13 days, 18 days, or so on. You might not be able to decide. Okay, so each one of these is a Pareto-Optimal solution. There is no dominant maximum. Another thing that you will see probably in the literature a lot is when you do it like this, instead of doing it this way, you have two axes. So one of them here can be luxury, and the other one could be vacation time. So you have both of these goals as the two, each one of them as one axis of your problem, and then the parameter that you can select, you can have it an implicit parameter. So if you look at that, then of course, the more days that you work, it means the less what? The less time you will have for vacation, and but more luxury. And the less time you have to spend on work, it means more time you have on vacation, but less luxury. So you might have something like this. Okay, and maybe you do not want any of the higher ends, so I do not want a lot of time with no luxury or a lot of luxury with no time. But here, maybe this range from here to here is either way. I can go both ways. I can spend a little bit less time, but do more luxury things, or what? Spend more time, a little bit less luxury. So any solution here on this range might be called what? A Pareto-optimal solution. Okay, so I do not, I cannot really decide. There is no dominance here. Finally, the last thing is called convex functions and convex sets and convex optimization. So convex optimization is minimizing convex functions over convex sets. But what is a convex function? What is a convex set? So I explain them very simply. So a convex set or a convex area is an area that if I connect 2 points inside that set or inside that range together using a line, the entire line falls within the set. If that is valid for every 2 arbitrary points, I can say this range or this set is convex. In this case, it's not. Why? Because if I choose a point here and a point there, and if I connect them together, you clearly see that some portion of this connecting line is outside my range, so this is not a convex. But if the shape is something like an ellipse, like a circle or so, it does not matter where you choose your points. Any 2 points you choose arbitrary, the connecting line is entirely within the set. So this is a convex set or range. This is non-convex. Okay, so this is convex and non-convex set or range. And a similar thing can be said about functions. A function can be called convex if what? So if I have a function like this, and if I choose any 2 points on the function, and I connect these 2 points together, the connecting line is, as you can see, it is above the function, right? So if you look at the range of the function between these 2 points, and if you look at the line is above the function. So this is called the what? This is called the convex function. Again, the line connecting any 2 points on the function is above the curve itself, right? But if I have something like this, can I find 2 points that if I connect them together, the line is not entirely above the function? Well, absolutely yes. Like where? Like, for example, a point here and a point there. If I connect them and look at the range of the function between these 2 points, you see somewhere the curve is above the line, somewhere the line is above the curve. So this is a what? This is a non-convex function. Okay, so that's the difference between convex function and non-convex, convex set and non-convex. So if my optimization is to optimize a convex function over a convex set, we call it what? We call it convex optimization. And what's special about convex optimization? The specialty is solving convex optimization problems are much easier. There are way more analytic methods and way easier, more convenient solutions to these problems compared to the cases where the function is not convex or the set is not convex. Solving these type of non-convex problems is typically way harder. Sometimes there might not be any definite optimal solution. All you might end up with is just a feasible solution. So convex optimization is kind of like in controls, you do linear controls. In linear controls, you have a lot more analytical tools and ways to solve your problems. In nonlinear control, your tools are very limited. The same thing with convex optimization, which is like the gold standard simple optimization versus non-convex, which is the hard version, okay? So just wanted to tell you these important terminologies about optimization that we are going to see a lot in the future lectures. So thank you so much for your attention. I will see you in my next video where we talk about the Levenberg-Marquardt algorithm. Thanks.